www.nanohub.org. You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
Let's get started. So this is lecture 26 on Schottky diode. This is the second part of the lecture where we'll be talking a little bit more in detail about the Schottky diode. In the last class, we talked about why Schottky diode is historically important. Remember, this was the first diode that people used much before they knew anything about semiconductor or how semiconductor and metal junctions work. This is before quantum mechanics, before spatial relativity. This is very, I think in the 1890s or so, that's first when they started working on this. But still, even today, in scanning tunneling microscope and for a wide variety of other situations, this device is still very useful. And for many practical devices, even inadvertently, this is important, as I'll explain a little bit later. Now today we'll talk about a little bit more detailed about some aspect of Schottky barrier diode, and let me get going. So the first thing I'll be talking about is the thermionic emission current. This current, you'll use this formulation anytime there is a discontinuity in the conduction and valence band. If there is a discontinuity, then you want to actually calculate current always using this thermionic emission formula, where you take a flux from the right, a flux from the left, and then use the ballistic transport essentially to connect the fluxes across the junction. This you always have to do anytime there is a heterojunction. Now I'll do a little bit more detailed derivation. The last class we did a simple one and that was good enough. We will talk a little bit more today. We'll talk about a little bit about AC small signal response. Now this is very important because it is fundamentally different from PN junction. This is a majority carrier device. You do not have any diffusion capacitance in this structure. Anytime you have minority carrier injection, then minority carrier response, you have a large diffusion current. And therefore, diffusion capacitance is a very important component. Nothing like that here. So we'll see that these diodes are actually very fast. Talk about few more things and then especially surface states, and then I'll conclude. So when you want to calculate current across this heterojunction, here the structure is such that the metal side has been grounded. The metal is on the left hand side, and you see I have just shown one line because that's the Fermi level inside the conduction band. I have not shown the edge of the conduction band, which is much below. And of course, even in metal, there is always a band gap, but that's farther down. So that's why we have not shown those things in this picture. You also know that there is a slight band bending on the metal side at the junction. That I have not shown as well. It's because the metal concentration, carrier concentration is so high, 10 to the power 20 per centimeter cube easily. So therefore, the amount of depletion and the band bending is minuscule, has not been shown in this particular picture. Now in the last class, we looked at the two fluxes and calculate the current easily. Let's look at this a little bit more detail so that you understand how these calculations proceed. If there is this device has been forward biased because the metal has been semiconductor side is N, and the N side has been connected to the negative terminal of the battery. That's why the Fermi level has been pushed up. And the net barrier has gone down from VBI to VBI minus AA. VA is applied bias. And you know these two fluxes. And these red and the blue fluxes are of course going in both directions. But as far as I am interested in the calculating the flux at the interface, I just take half of the fluxes that are going in the opposite direction. So generally you should really calculate use a formula like this. It is exactly the same as the simple formula that I showed you before, but a little bit more rigorous. Let's go through it slowly. I have shown here three integrals over kx, ky, and kz. You can see volume divided by 4 pi cube. Where have you seen that thing before? That is the shell, right? Remember density of state. In that calculation, we had a shell for k and k plus delta k, and we divided into small cubes. Do you remember that this must have included spin, because it is 4 pi cube, not 8 pi cube, because I have already multiplied by a factor of 2 for the spin. And this, therefore, is indeed, if I didn't consider anything else, and if I wanted to look at the density of state at a given point kx, ky, kz, then that would be my density of state. And you have done this homework also, right? Do you remember that instead of looking at a shell between E plus delta E, there was also a homework where they asked K plus delta K, Kx plus delta Kx plus Ky plus delta Ky, Kz plus delta Kz. You had that homework, and this was in preparation for this calculation. Now that's the density of state at a given value of K. Then this is the occupation, this is the Fermi occupation. Now, of course, this only applies if it is degenerate, or sorry, non-degenerate, because then you can make this Boltzmann approximation of the Fermi-Dirac distribution. Beta is 1 over kT. Now, the reason I write it out this way rather than simply calculating the density of state multiplying by the Fermi factor is because there is something special about the velocity for this electron, and you can see that. Notice that if an electron is going from, let's say, right to left in the x direction, then it has a chance that it will go over the barrier and will contribute to the current. But if I had an electron which is going along the y direction, perpendicular to the junction, well, it can keep going forever as long as it likes, but since it will never cross the junction, so therefore it will not contribute to the current, right? And similarly in the kz direction, in the z direction, the electron could go forever, but because it is never crossing the junction, it is not going to contribute to the flux. As a result, I cannot simply just integrate them all out and call this is the density of state multiplied by this velocity. You see, the reason is, of course, not all those electrons going in x, y, and z direction are going to cross the junction, and they will not contribute to the current. So I write it resolved in x, y, and z, and look at the velocity I have multiplied with, Vx, because that's the only part of the flux, that is the only part of the flux that is going to contribute to the current. Now, you also see that I have put the look at the limits. In particular, other limits are infinity to minus infinity, whether electrons go in the plus direction or minus direction at whatever velocity, that's fine. They are not contributing to the current directly. But look at the velocity that for the velocity along the x direction, I have a limit which is minus infinity is fine, that if you have a lot of energy, of course you can comfortably go over the junction. Nobody is stopping you. But by the way, this cannot be infinity really. Remember, all bands are finite. So we am talking about bottom of the band to whatever is the top of the band. That's what it is. Now, for semiconductor, bands are about a EV or so. So that is about infinity. But there are many organic semiconductors that people are using for displays these days, which has a very tiny band distribution or band width. In that case, putting the right limit, not minus infinity, would be the right thing to do. Okay, but what about Vmin? Well, Vmin is, you can see that Vmin is essentially talking about that unless it has a minimum amount of velocity or minimum amount of energy, then an electron going there will be bounced back by the barrier. and as a result it will not go, cannot contribute to the current, and as a result it should not be included in the flux. So that's where the limits come from. Now this looks like a horrible integral. Actually it's not that bad, especially if you know the answer ahead of time. Similarly, for the blue side, you can see that there will be a barrier which will reflect the carriers, and that's independent of bias, because no matter what you do to the right hand side, because there is almost no band bending in the metal side, so that barrier where the blue is turning back, that barrier is almost independent of voltage. We discussed this in the last class. So now let's look at the Fermi factor, E minus EF. E is some energy above EC, and you can see EF, and that's the occupation, right? Fermi function or the Boltzmann function at a given value of energy, that only depends on E minus EF. So you can split it into two pieces. E minus EF, you could say, okay, I have two pieces. One is E minus EC, right? From the age of the conduction band to the energy of the electron, and EC minus EF. Just these two pieces. Now E minus EC, what is that? That's the kinetic energy. Do you remember that we did this kinetic energy and potential energy business before? So E minus EC is the kinetic energy. So I should be able to write it as half mv squared. Now m star, of course, because this is effective mass, right? Because it's taking into account all the electrons or all the atoms that are around it. So m naught, but other than that, half mv squared. And I have kept the EC minus EF just as is. Now EC minus EF, that value only depends on the doping. So long you have a doping of a semiconductor, somebody told you what the doping is, EC minus EF is a number, you can take it out of the integral, you don't really care about it. So this is what it is. So you can see I have this EC minus EF, I have pulled it out of the integral to the left hand side. Do you see that half mv squared is sitting on the exponential? I should have written an m star over here in general. Now, then of course, I have written the dkx. Kx is h bar k is mv, because h bar k is the momentum, mv is also the momentum. So I can write it as m star vx divided by h bar. That's it, and I can pull it out. I can divide this because you can see each integral, although there is this three pieces of integral, each you can put it in their separate boxes and try to integrate them out. You can see the y and the z pieces look very similar. They are exactly the same, something sitting on the top of an exponential dv, and you integrate between minus infinity and plus infinity. But the x integral is slightly different. Do you see? It carries with it extra vx. The limits are funny from minus infinity to minus v min. So that we have to be a little bit careful about. The remaining two pieces are actually very simple. Okay. So what should the values be? Well, turns out that if you look up in your integral book, then you will see that the first one is actually just a square root of pi. That's the first one. And the second one with some factors, And the second one, after you have e to the power x squared, then dx. So within some factors is square root of pi. And the last factor, because once you insert the expression for v min, do you see why that should be the value of v min? Because v min is related to the barrier height. Half mv squared is that v min must be at least equal to vbi minus va. So therefore, I have that expression. I will put it in as the top limit, and once I have done that, if I do this integral, I will pull back out this, the limit will come here in the exponential, and then that will be the final answer. So once I pull everything down, all those extra factors down, this is the final result. The final result has a bunch of constant, goes as t squared, EC minus EF, VBI, and you can see I can put all those prefactors up front as A naught and QVBI, QVA divided by KT. Very similar to the PN junction flux, you see, exponentially increases with applied bias. Very similar, but also very different. If you remember metal semiconductor, if you remember the PN junction and the expression for it, do you remember that upfront for the minority carriers there was this Ni squared divided by Na, Ni squared divided by Nd, that was a prefactor? That prefactor says that PN junction current is extremely temperature sensitive. Why is that? Because Ni squared has exponential of Eg over Kt, and the band gap, because Nc, capital N, capital Nc, capital Nv, e to the power Eg over Kt, right? And the band gap itself is extremely temperature sensitive. As a result, the prefactor is very temperature sensitive. On the other hand, here, I do not have the band gap explicitly sitting there. Of course, band gap is hiding somewhere, and we'll talk about that in a second. But in general, since there is no Ni squared term, so therefore, although the expression looks almost the same, it is much less temperature sensitive. Now, what about, now you should try to work it out, because I have just shown you a square root of pi over there, but I haven't accounted for all the constants that we'll need. Do this when you go home, and you will try to see whether you can pick up all the constants. Now, that's one thing, that difference between PN junction and a Schottky barrier. There is, of course, you can always calculate the current. Remember that at zero bias, the current from semiconductor to metal must be exactly balanced by the current from metal to semiconductor. So you set a VA equal to 0. So the current from metal to semiconductor will simply be A naught. And so the net current is A naught e to the power q VA beta minus 1. Beta is 1 over KT. Now, just wait for think about a second about where quantum mechanics is hiding, where is the information about doping, and where is the information about the fact that I have a pair of metal, let's say aluminum with germanium. Where is this information in this expression? Okay, so one is you can see M star. M star is sitting there. So quantum mechanics is there, and that will contain the information about whether it's silicon or germanium, whatever the semiconductor is. Now, where is, and you can see the doping, where is that? EF minus EC, that is where the doping of that semiconductor is hiding. That's fine. Now, what about the band gap? How do I know that this is a particular metal or particular metal semiconductor configuration that has a certain band gap? Where do I get that information? That is hiding in VBI. If you remember the info about VBI, do you remember that had on one side chi sub m from the Fermi level to the vacuum level? On the other side, we had the chi plus VBI plus the doping. So that actually contains the information about what pair of material it is, and as well as what type of barrier and other information you have. Deriving an expression, these are not complicated things, but you should be able to come back and say that if I change my material, let's say somebody is saying I want to do, no, I don't have aluminum deposition, I want to do copper deposition today for some reason. You should immediately be able to say, what is it in this expression that you are modulating? Of course, you cannot modulate VBA, that's your AAA battery from outside, but you can modulate the constant up front. That's your design of the devices. So what I explained so far is this IV characteristics in the diffuse or in the thermionic part of the device, right? And you can see the slope of that region is Q over KT as soon as the applied voltage is a little bit high, because then the -1 will be negligible, and then you can do a log linear plot, and that will have a slope of Q over KT, very similar to the diffusion in the PN junction. Do you remember that? Okay. Now, you can also do other things. Many times these devices might have a lot of traps between metal and semiconductor side. And so in that case, what will you do? You will just take the previous expression, exactly the same expression for p-n junction, and realize that dn dt will be your p-n junction, just like your p-n junction, the recombination, and you will integrate between 0 to Wn, because that's the depletion width, just like we did before. And you will do the recombination in the forward bias junction. Now this is something you have also done at homework, that when you have a forward bias junction, what the depletion width is, and correspondingly what is the integrated Shockley-Rittal recombination. So you have done this before, and that will give you a recombination generation dominated region that has half the slope of the thermionic current region, right? Why is it? Because it's the electron and hole concentration both has to balance at the point of maximum recombination. Therefore, this extra 2q over kt, that's where that comes from. What about on the reverse side? Reverse side, again, you know that this is exactly the same. This time this is reverse biased. So instead of recombination, in this depletion region, you will have generation. So generation is, what is that equal to? Minus Ni divided by tau, or 2 tau, right? So essentially, we will just have to integrate that. And once you integrate that, only thing you realize that this is increasing. The width of the depletion region is increasing with square root of V. And as a result, my current will also keep increasing as the square root of V. What about that last piece? Impact ionization. Or what was the other thing? Zener tunneling. Well, both can happen here. What's wrong? If you have higher bias on the positive, let's say you put a high reverse bias on the semiconductor side, the electron can easily tunnel in. You can see the triangular barrier. Don't you see that? On the left hand side, I have huge amount of electrons, full of electrons on the metal side. And it can easily tunnel through that triangular barrier to the semiconductor. And therefore, I can have a huge amount of current, just like a p-n junction. Similarly, I can have impact ionization. That is, a carrier may be emitted or generated in the depletion region, and then it may start rolling down the barrier, and in the process, if it has high enough energy, then it will generate its pair, and this process will continue, and then you will have an avalanche multiplication. Exactly the same physics that we have discussed for p-n junction. So I wouldn't go into that. You will see exactly the same thing. So just remember, this is a one-sided junction. That is the important thing, because there is no depletion on the other side. So apart from that, everything is exactly the same. Now let's talk a little bit about AC, small signal. Now in the small signal case, so everything I discussed is like DC. You know, all the currents look the same, but the thermionic emission current is a majority carrier. That's why not very temperature sensitive, relatively speaking, compared to p-n junction. All other parts, this region 1, 2, 3, 4, 5, 6, those are all exactly the same as we have done in p-n junction. Now the AC response is very interesting because it's very different actually. This is again a metal semiconductor diode, N-type, contacted with the metal, the dashed region, and you see that you have a AAA battery, that's the VA, and let's say you have the radio, your favorite radio signal, that is in a microvolt or so, and that is the small VA, and as the bias is modulating with that small VA, sometimes it's a little bit more forward bias, sometimes a little bit less, so it's oscillating, right? The net bias is oscillating, and so therefore there will be a current that will oscillate in response. And again, in principle, you should have all this conductance at that bias, governed by the DC bias. The junction capacitance, well, that I might have, but the thing is that I will not have a diffusion capacitance here. And that's what I want you to understand, why I don't have a diffusion capacitance. And therefore, this device is very fast actually. So how will you calculate the conductance? Well, the rule is the same, because you know the equivalently you have the same expression. Beta is kT and m depends on whether you are in the thermionic emission part, you know, then it's 1, or you are in the trap recombination generation dominated part, then m is 2. And in that case, so you will put the relevant expression for m in the region you are operating, right? Whatever is your DC bias, that point will automatically tell you what is your m at that point of operation, right? So you have a value of n, you take a derivative, first you take a log, bring the I naught on the other side and take a log, and then take a derivative with respect to the current, and as a result you can get an expression for the forward bias conductance. And forward bias conductance, you can see that has a series resistance Rs. What is this series resistance coming from? This is for the electrons as they are coming from the contact all the way to the junction, all the resistance in between, that is the series resistance. Because remember, that's not what we have accounted for so far. Only thing we have accounted for so far is what happens in the junction. But if I have a 1 meter long wire, copper wire, of course, even before coming to the junction, that 1 meter long wire will have certain resistance. Same for the semiconductor side. So I will have that, and you can correspondingly calculate what the forward bias conductance would be. Okay. What about the junction capacitance? Well, do you remember the junction capacitance is always associated with majority carriers, that as soon as you start sort of changing the voltage across the two ends of the junction, in the majority carrier side, the pulse immediately comes to the junction side, given by this, what is this time called? Dielectric relaxation time. Because when you have a majority carrier, the way the response propagates is not, an electron doesn't go all the way through. This electron tells its neighbor that I have been pushed, help me. That one says to the next, and that propagation is extremely fast. That's why when you turn on the light in the room, then you don't really have to wait before the electron himself goes in the bulb and says, let's turn on. But rather, each pushes the other, and eventually this propagates very, very fast, on the order of less than a picosecond. So unless your computer is operating at a terahertz, then you really don't have to worry about this propagation time, because that's very fast. And the junction, again, the bias, when it's a little bit more, your junction is a little bit less. When it's a little bit less, your junction is a little bit more. And so this, on one side, there is metal, electrons coming from the one side. The other side, the majority carriers are coming, and this bounces back and forth at the junction. Majority carrier phenomena, and therefore you calculate the majority carrier capacitance. A, epsilon A over W, but W is just the depletion width, whatever the depletion width. And you know, we have calculated the W, that if you apply a forward bias, W goes down, right? And then if you have a reverse bias, the W will be larger. But that's the point. You generally get the idea. You can easily calculate this. Now, the main point is that there is no diffusion capacitance in Schottky diode. This is because of this following thing. In Schottky diode, there is no minority carrier. If you don't have a minority carrier, nothing is diffusing, because as soon as it comes in the other side, where it could be a minority carrier, it immediately joins the majority carrier. You know, you come to a new country, and instead of keeping your identity for a while, you sort of blend in with the majority, and in that case you can enjoy all the facilities or the transport advantages that you have with the majority. It's the same thing here. And the reason it happens is because as soon as the electron comes in, when it's this much high in energy, it has no band gap or anything, right? In this region, phonons will immediately scatter it down, as if it has recombined with the majority carriers immediately. As a result, it is not sitting up there sort of slowly responding and diffusing. As a result, you do not have any diffusion charge, And if you don't have any diffusion charge, as soon as the charge comes in here, then it responds with the dielectric relaxation because it's a majority carrier. And I do not really have to wait for the electrons to gradually go back and forth and respond with the minority carrier lifetime. So this is about Schottky diode, and this is, I want to emphasize, very different from the PN junction diode, where you can see the red triangle on the left hand side is the minority carrier. Unless you have a lot of traps sitting there, then it stays on the minority carrier side for a long time. As you bounce your potential up and down, then the string, the blue wavy line, that says that how it diffuses. Each individual electrons needs to go, and that takes a lot of time. So therefore, it's actually a slower device. Now, you could make the PN junction diode almost as fast as the Schottky barrier if you do this. Many times people will intentionally put in defects on the minority carrier side. If you do that, then what's going to happen, that as soon as the minority carriers goes there, then the defects will allow it to join, to provide a sort of a byway or a shortcut to join the majority carriers. And if it can join the majority carrier first, then the amount of stored diffusion charge on the minority carrier side is very small, and as a result, this could respond as fast. And that's what many times people do in terms of if they wanted to make something very fast, a PN junction diode very fast. This is something people have done. Historically, people have done. I do not know whether they still do it. They might still do it for some specialty devices. I do not know exact examples where they are still used. So let me talk about a few things about these metal semiconductor junctions. Metal semiconductor junctions are everywhere. If you have a metal, let's say even when you talk about a PN junction, or any junction whatsoever, you always have to connect at that end of the day with metal, right? And if you are connecting with metal, right, there's a wiring. If you want to wire things up, then you will always have a barrier. Now the question is that if you have that barrier, then how is current going to flow? You don't want that anytime you put a metal down, that there is a barrier, because then current may not flow unless you apply a bias. So what do people do? If you do not want the metal semiconductor junction to bother you, because if that is not the main purpose of your device, let's say you're doing a normal PN junction diode, normal, and then you have to put metal on both sides. Now then another two Schottky barrier diodes, Schottky barriers are sitting on the top and the bottom. You don't want that. You just want the PN junction. In that case, only recourse you have is to dope the N side very heavily. That's why you see that in the purple region, I have shown N+. N+ means very heavy doping. And what it does is that when you have very heavy doping, then the electrons don't have to go over the barrier. They can just tunnel through the barrier. And as a result, the resistance may be minuscule in that case, because they can just go through the very thin triangular barrier region. Now that's for one type of carrier. Do you see, although it has problem with those electrons, if you wanted holes to come in and out, you do not have a barrier for the holes to come in and out. Do you see on the bottom side that if the hole wanted to come in and out, there is no barrier. So the hole transport is always ohmic. Ohmic means linear dependence with voltage, no exponential dependence with voltage. So on the one side, for the minority carriers in this case, no barriers, so they can easily come in and out. Now for the majority carriers, there is a barrier, but you can get rid of that effect by doping it very heavily. And that's what the tunneling is. In an ultra thin barrier, electrons will tunnel, and so although it has a barrier, but it will behave as if it had nothing. And that's called an ohmic contact. So people will often ask you that, are you sure that you have an ohmic contact? They are asking that whether you have treated the contacts properly so the Schottky barriers is not disrupting your flow of electrons. There's another thing that is also sort of you'll see in various textbooks that people talk about, although I do not know how important this is, and that is something to call lowering of the Schottky barrier, and this is what it means. When you have an electron in the top, let's say a red electron trying to get out to the metal side from the semiconductor, I have so far assumed that this is like free electron going from one side to another. But you remember that I'm going to a metal. Do you remember that if I have, let's say from undergraduate years, forget about this particular situation, that if I have a metal, then if I have a charge sitting on top of the metal, then the electric field must terminate vertically on that surface. Because if I had even in a tangential component, current will flow in the metal, and current cannot flow. There cannot be any potential difference. So it must terminate vertically. That means there's always sort of effectively an image charge on the other side. Anytime I have a charge on top of a metal. So that is what I have shown here, that anytime the electron is moving, the red electron is moving towards the metal, it induces the surface charges on the metal, right? Because it must terminate perpendicularly. As a result, I could, instead of replace the metal with a corresponding equivalent image charge. So if I have an electron on the red, what will be the sign of the yellow one? That must be positive, right? Image charge is always the other polarity. And so I have a positive and a negative charge. They must attract each other. As a result, effectively speaking, as a result, the red electron will get an extra pull to pull it out of this semiconductor. As a result, what's going to happen, that look at the barrier. When you combine this extra electrostatic pull, then as if the barrier has gone down effectively, because the electron can pass out from this here a little bit easier. And so that's why that barrier is a little bit lower than what you would have otherwise would have thought about. If the other side was a semiconductor, then you wouldn't have this effect. As a result, this extra lowering of the barrier is sometimes very important. Remember, this is exponential in the barrier height, the current, exponential in barrier height. So although it's tiny, it may be like several hundred millivolts, but that on an exponential can change your current quite a bit. So therefore, many people discuss this as an important effect. Now, this is a topic I have not worked personally. Most of the other things I have worked in my career sometime or other. So what I'm saying is sort of a little bookish in the sense that that's what they discuss in the book. I do not know for sure that how important some of these things are. There's a reference in the Z's book and page 143 that you can look up. Finally, it's something about called Fermi level pinning, and the Fermi level pinning is a very important recent phenomena, and let me explain to you that why anytime you bring a metal to a semiconductor and push them together, you may not always get conduction at all. Conduction, you have to do something very special about it. The reason is that semiconductors are a very special thing. When you terminate a semiconductor, right, make it finite, do you not have a lot of interface states? Do you remember the surface recombination velocity and all those states sitting in the mid gap and the recombination that we talked about? Of course, those are all there. I mean, simply because I haven't drawn it doesn't mean they do not exist. And so what happens that near the edge of any semiconductor, there is a lot of surface states, as if you have this NT is the number of traps, right? Like you have a lot of traps, like as if you have a lot of doping in the end of this region. Because if you solve for the position of the Fermi level in the presence of the surface states, then you will see the Fermi level is very close to the middle because we have so many traps. As a result, you see that the red region I have shown with sort of a Gaussian curve, that is somehow to represent the presence of the surface states. And when you have that amount of surface states, it pins the Fermi level to the middle of the band gap. regardless of what you did internally. It may be a heavily end-doped region. Really, it doesn't matter because EF could be close to EC near the middle, but near the edge, the doping essentially they have been taken over by the surface states. As a result, what happens often that if you are not careful and don't treat this surface states properly, then even if you, so let's say in one side the metal, on the right hand side metal has a given work function, on the left hand side let's say metal has a different work function, but it wouldn't matter. The reason is that even when you bring them in contact, what's going to happen that the interface region will exchange carriers with the metal and will not tell anything to the semiconductor because that has enough electrons. As a result, what's going to happen that the barrier, the net barrier, will not be modulated by the choice of your metal, which is a horrible thing, right? Because you wanted to design a transistor that changes with the metal as you change the metal. But if it doesn't respond, because it's like a gatekeeper, you know, this surface states are like gatekeepers, and the gatekeepers are all absorbing and talking to the metal on the other side, not letting the bulk of the semiconductor know. As a result, the depletion doesn't change, and as a result, the modulation doesn't occur. So this is a very bad thing. Historically, Bardeen was the first one who explained it in 1940s as why many of the devices do not work. But even today, even this year, if you go to conferences, you'll hear this term Fermi level pinning, because many modern transistors, they are trying to put high K dielectric on the device and then on top of it metal, and they are worried about Fermi level pinning because most companies cannot solve it properly. And that's why many companies cannot introduce high K products with metal gate in the marketplace. This same problem. But there are solutions of various sorts. But this is something important to know about metal semiconductor junctions. So let me conclude. So as I said, Schottky barrier has wide range of applications, and this is very practical device. But more importantly, metal semiconductor junctions are everywhere. You always have to connect your transistor, whatever, carbon nanotube, spintronic device, whatever you have. You always have to connect them with metal. And so metal semiconductor junction, whether you like it or not, it's always there. And you have to handle it properly. Now, one distinguishing feature from PN junction is a majority carrier device, no diffusion capacitance, and therefore, and also no strong temperature sensitivity, which is a good thing. And you realize that because I had this heterojunction, not because it's metal semiconductor, but because I had a hetero discontinuity in the conduction band, I had to use thermionic emission. Anytime, next time you see a discontinuity, regardless whether it's a metal semiconductor or two semiconductors, you know, germanium and silicon, a discontinuity in between. Near the junction, thermionic emission current. That's how you should calculate it. Now, one final point I want to make about this, I have talked about semiconductor. I've talked about metal to semiconductor. The question is, can you draw a Venn diagram if you had metal to metal, copper to aluminum, if you put it? Will there be a barrier, you think? Actually, there will be a big barrier. If it didn't work, then your thermocouples wouldn't have worked. Why should be this, where this band gap would be coming from? Because one side you have phi of M1 and another side you have phi of M2. You'll use the same rules I have told you about, flat Fermi level and then vacuum level on the two sides. Make them continuous, pull them down. The VBI that you will see even in a metal case is always there. That's why when you pump a current through metal junction, you have this thermocouple where energy can be gained or lost. You know, there's various types of thermocouples people can buy. So that part I'll not discuss in detail because for semiconductor physics that's not important. But as a concept, that's very important that you understand semiconductor metal, and metal, how they behave together. Okay, thanks.